Well, welcome everyone. I'm Mike Wong, a postdoc in astronomy and astrobiology, and I'd like to center ourselves with this quick land acknowledgement. So we acknowledge that the UW Astrobiology program resides upon the land of the Coast Salish peoples, land that touches the shared waters of all tribes and bands within the Duwamish, Puyallup, Suquamish, Tulalip, and Muckleshoot nations. And we recognize that we, the UW Astrobiology community, benefit from the occupation and use of this land, and that it is our responsibility to mend and forge our relationship with Indigenous peoples who are extant and vibrant members of the broader Seattle community. And I'll put some helpful links to resources in the Zoom chat window if you'd like to learn more. Okay. And now it is my distinct pleasure to introduce you all to Professor Myriam Telus. Dr. Telus earned her bachelor's degree in geophysical sciences from the University of Chicago and her PhD in geology and geophysics from the Hawaii Institute of Geophysics and Planetology at the University of Hawaii, Manoa. She then went on to become a Carnegie postdoctoral fellow at the Carnegie Institute's Department of Terrestrial Magnetism, and Myriam is now an assistant professor in Earth and Planetary Sciences at the University of California, Santa Cruz. And she's the recipient of the 2019 NASA Planetary Science Early Career Award. And today I also learned that she's a big fan of Star Trek Voyager, so I wish I could also award her the Mike Wong Award for impeccable taste in TV shows. I know, it's not quite as prestigious as a NASA award, but still. Myriam is an expert in planetesimal formation and evolution, and today she'll tell us about meteorites as analogs for planetesimals in extrasolar systems. So Myriam, welcome. The floor is yours.
Thank you for that awesome award, Mike. I've never received an award for watching Star Trek. That's awesome. You should actually make that a real award. Okay, so let me get myself situated here. And okay, let me know what you can see. What do you see?
That looks good. We're seeing your title slide.
Okay. Hello, everyone. Thank you for inviting me to meet with you today and discuss this work that I've been doing since starting at UC Santa Cruz. It's also been a pleasure to meet with some of you one-on-one, especially the grad students. They were great. We had a fun conversation. So thank you again. So my research is in cosmochemistry. My work focuses on understanding the meteorite record of planetesimals, and I use a variety of geochemical techniques. So meteorites are extraterrestrial rocks that fall to the Earth from space, and most of them come from asteroids. Asteroidal meteorites, like this one pictured here, they provide a geological record of the earliest stages of solar system formation from the components of the molecular cloud and to the formation of planetesimals, which are the building blocks of planets and their atmospheres. I'm interested in understanding planetesimals as a record of the conditions in the solar nebula. So like this illustration is showing that with time, so this is 0.3 million years after solar system formation and to 300. But over time, most of the planetesimals, which are pictured as these small dots here, they either accreted onto the sun or they went into forming larger bodies through collisions between planetesimals and protoplanets. Ultimately, this whole process resulted in the solar system structured more or less as you see it today. So for my work, I utilize various geochemical techniques to analyze meteorites to understand the timing of planetesimal formation and the conditions in the disk that influence the diversity and compositions of planetesimals. I'm also interested in meteorites as a window into the early processes that shape terrestrial planets. So I'm interested in how planetesimals influence the composition of terrestrial planets. I'm especially interested in this as a way to help interpret the chemical signatures of exoplanets. And so, like, exoplanets are part of the key to finding evidence for life beyond Earth, but we have to better interpret, we have to be able to interpret the chemical signatures we see in their atmospheres. Since the discovery of exoplanets, we know planets are common across the universe. So this means also that planetesimals are common as well. So we can use our knowledge of planetesimals to help us understand the extrasolar planetesimals and planets. So for this presentation, I'll discuss meteorite outgassing experiments as a tool to constrain the volatile inventory of planetesimals. And I will discuss some important considerations, basically questions that I've gotten over the years of trying to discuss this work with other people, especially the question regarding the relevance of meteorites for understanding planetesimals in extrasolar systems. So in order to constrain the inventory of gases that planetesimals can potentially contribute to a growing planet, we developed a method to measure the gases released as meteorites are heated. This work was carried out by my PhD student, Maggie Thompson. Maggie's manuscript about this work was recently published in Nature Astronomy, and so you'll see basically figures from that publication here. This study was developed through an interdisciplinary collaboration with researchers in astronomy and material science and planetary sciences at UCSC. And we also have collaborators from Stanford and Carnegie. So astronomers could now tell whether or not an exoplanet has an atmosphere, and they're beginning to probe the composition of exoplanet atmospheres. State-of-the-art space telescopes such as TESS and JWST, along with ground-based telescopes, will significantly increase our inventory of rocky, Earth-like exoplanets that have and the chemical signatures of their atmospheres. But how can we determine if an exoplanet is habitable from atmospheric observations? So I will discuss how heating meteorites in a furnace can help us, can provide tools basically to help us better interpret the atmospheres of exoplanets. So there are a number of processes that influence the formation and compositional evolution of a planet's atmosphere. These include radiation, the radiation environment, which influences photochemical reactions that take place in the atmosphere. It also is important for controlling the rate of atmospheric escape. Large impacts are important. They can potentially add volatiles to a growing planet, or they can take them away by stripping the planet of its atmosphere. Volcanism and plate tectonics also affect the composition of a planet's atmosphere. This controls the cycling of volatiles from the interior of a planet to the surface. And of course, the presence of life on a planet affects the composition of its atmosphere. For example, certain bacteria can potentially influence the abundance of methane in an atmosphere. But the bulk composition of the atmosphere is necessary to understand in order to understand how these other processes affect the atmosphere. So our meteorite outgassing analysis allow us to put stronger constraints on the bulk composition of an atmosphere. and linking the composition of the atmosphere with the bulk composition of the planet. Full characterization of exoplanet atmospheres still relies heavily on models. So exoplanet atmosphere models require input of stellar and planetary parameters such as the effective temperature of a star and the surface gravity of a planet. These models then produce pressure temperature profiles and model spectra of exoplanet atmospheres. And the model spectra is then compared to the observations. So here is a comparison between the model spectra and observations for an exoplanet. The plot shows the observed radius of the exoplanet versus the wavelength of the transmission spectra. And the curves, these different curves here, are the atmosphere evolution models under different conditions. And and so that's compared to the data shown here. These models require input for the bulk composition of the atmosphere. So this is often assumed to be solar or some multiple of solar. So in this case, they use 50 times solar as the bulk composition of the atmosphere. Basically, they found that 50 times solar provided the best match to the data. So, and this assumption is fine for giant exoplanets, which accrete atmospheres directly from the nebula, but this is not the case for terrestrial planets, which produce atmospheres from outgassing of the rocky material. So our meteorite outgassing experiments will be helpful for providing constraints on these types of models. The bulk composition of a planet is an important parameter for constraining the initial inventory of volatiles that go into building a planet's atmosphere. So the bulk composition is controlled by the composition of the planetesimals, so the building blocks of the planet. Meteorites provide the geological record of the population of planetesimals that went into building the planets in our solar system. And they can potentially help us understand planetesimals and terrestrial planets in extrasolar systems. So meteorites tell us that there are overall two types of planetesimals during solar system formation. There were chondritic planetesimals that did not experience enough heat to cause melting and differentiation. And so because of this, these planetesimals were volatile rich. And there were the differentiated ones that separated into a core and a mantle. And these experienced enough heating to cause global melting. And so they were more depleted in the volatiles. And so depending on the composition of the accreting planetesimals onto a growing protoplanet, the formation of an atmosphere could result from outgassing of volatile species released during this highly energetic planet building process. Just a little bit of background on meteorites. So most meteorites are from asteroids. And so these are remnants of the rocky planetesimals that formed in our solar system. They occur in a wide variety of compositions, and they have a range of physical properties. Some examples are shown here. Their irregular shapes and crater surfaces indicate that the asteroids have been battered and reconfigured by billions of years of impacts. And so it's not clear exactly what these planetesimals originally looked like. When we examine meteorites, they provide many details about the composition and thermal history of planetesimals that were available for building planets. So there are three different types based on looking at meteorites. So the differentiated ones, which I mentioned earlier. There's also the metamorphosed ones, chondrites that have experienced heat but have not melted. and then primitive ones that have experienced very little heating. So, and the degree to which these planetesimals have experienced heating is related to the amount of aluminum-26 that was incorporated during the formation of these planetesimals. And that's also related to the timing of their formation. So these differentiated ones formed early, and these really primitive volatile rich ones formed late. Meteorites come in a wide variety, which reflects the compositional diversity of planetesimals in the solar nebula. So here are some examples of this. This table on the left shows a list of different chondrite groups, and these are distinguished by their bulk composition. And then each group has a range in metamorphic properties, with those that have experienced more heating shown in basically listed here in red, and then those that have experienced more fluid alteration shown in blue. So you can see that some planetesimals have experienced fluid alteration, while others have experienced thermal metamorphism. Some of them have experienced both of those things. And then on the right is a plot showing the relative oxidation state for different meteorites. The oxidation state here is increasing from left to right. And from this, you can see that some meteorites formed under really reducing conditions, meaning relatively little free oxygen, and then others formed under more oxidizing conditions. So in summary, analysis of meteorites indicate that the compositional diversity of planetesimals in the solar system is influenced by the timing of their formation, and the conditions in the protoplanetary disk, and parent body processes such as heating, impacts, and fluid alteration. So the compositional diversity of meteorites make them important for understanding how volatiles from planetesimals influence the compositions of planetary atmospheres. Models of meteorite outgassing have been studied in detail by our collaborator, Laura Schaefer from Stanford. Her chemical equilibrium models of meteorite outgassing predict the composition of atmospheres produced by outgassing of various types of chondrites. So here you can see results for Ci/Cm type chondrites, or these are carbonaceous type chondrites, and then ordinary type chondrites. These are more, these have less organics and volatiles. So overall, they find that Ci and Cm chondrites produce water vapor rich atmospheres, while ordinary chondrites and EH chondrites produce hydrogen rich atmospheres. EL chondrites produce CO rich atmospheres, and CV chondrites produce CO2 rich atmospheres. This shows that chondritic material can produce a range of atmospheric compositions. Mubarak and Kempton applied the meteorite outgassing models from Schaefer and Fagley to exoplanet atmosphere evolution models to determine the type of clouds that could potentially nucleate in their atmospheres. And this is important because the presence of clouds can affect the type of spectra that is produced from the exoplanet atmosphere. So here you can see condensation curves assuming a Cm chondrite outgassed atmosphere, and that's on the left, and on the right, this one assumes an H chondrite outgassed atmosphere. The dashed lines are pressure temperature profiles for 2 super-Earth exoplanets. The condensation curves that cross the PT profile produce clouds of those compositions. So under these conditions, potassium chloride and zinc sulfide clouds would form in a Cm-like atmosphere. And then pure carbon clouds could also potentially form in a hydrogen, in a H chondrite atmosphere. Our experimental meteorite outgassing analysis can provide additional constraints on the parameter space for the compositions used to model low mass exoplanet atmospheres, especially in our experiments are more geared for non-equilibrium conditions. So more on our experiments. So for experiments, we heat powdered chondrite samples up to 1200 C under vacuum and measure the abundances of volatiles released as you increase the temperature. And we use a residual gas analyzer. The RGA is a small mass spectrometer. It's commonly used to detect contamination in vacuum systems. But it's especially suitable for our case because it's sensitive to trace amounts of gas. And so this system that's, the schematic is shown here, it's actually located in our collaborator's, David Lederman's lab. He's our collaborator from material sciences. So we can operate the RGA in two different modes. We can use the RGA in the analog mode to see where we basically scan the mass range from 1 to 100 AMU at specific temperatures. And then we use that to see what is being produced. What material, what masses are being outgassed. And so we use this to determine which masses to focus on for this study. And so you could see the list shown here. We can track up to 10 masses continuously. So and then in the continuous mode, we track these 10 masses, and you can see that some of them overlap. There's some overlap. So for instance, at 32 AMU, both 32 AMU could be both sulfur or O2. And I'll talk a little bit about that. For each run, we bake out the system, which means we heat it up and remove as much absorbed water, mostly. And then we run background analysis. We also run, and then once we do that, we also run the meteorite outgassing. So we do the experiment with nothing in there, and then we put in the sample so we could do background corrections. And so for this study, we focus on CM chondrites, and that's because they're really volatile rich. So they're like basically easier to study because they produce a lot of water vapor and other gases. And because they are some of the most similar in the composition to compared to the sun's photosphere. So the results from these experiments are the partial pressure for each mass as a function of temperature. The data for the sample is on the left here, and the one for the background measurement is on the right. So you can see the background is really high. So the other, so one issue we have to, besides overlap, which is I'll talk about later, but the RGA, the mass spectrometer we use, can fragment ions, which basically means that when the molecule hits the detector, it can fragment into it can fragment into smaller molecules that basically are not related to the meteorite outgassing. So there is a NIST database with fragment patterns of common molecules, and we use that to correct the data. So here I show the fragment patterns for water and methane. And you can see that water produces fragments at mass 16, which is also the mass for methane. So we must correct the sample data for background and for ion fragments. And then we also do a correction for terrestrial atmospheric absorption, so contamination from the atmosphere. So here's what the corrected data looks like after we make the ion fragment and atmospheric corrections. So sample data here and the background data on the right. Finally, we correct the sample data for the background, and we determine the relative abundances of outgas volatiles as a function of temperature for each sample. So that's what you see here. Our results indicate that if the bulk composition of the material being outgassed is similar to CM chondrites, then the initial composition of the outgassed atmosphere would be water vapor rich, along with significant amounts of CO and CO2. And also we have some hydrogen and hydrogen sulfide. Here, this is the thermochemical models from Laura Schaefer under the same temperature and pressure conditions as our experiments. And overall, the results are similar. However, we find significantly less hydrogen and H2S outgasses at higher temperatures than the models predict. In our paper, Laura basically did a calculation for us where she used this this initial outgas composition and calculated what the equilibrium composition would be, and it was even more similar if you do that calculation. But since our experiments do not simulate equilibrium conditions, it's not surprising that there are some deviations from the model. Our work indicates that the initial atmosphere of low mass exoplanets may differ significantly from many of the common model assumptions that are currently being used. Here, we're looking at the variations in specific elemental ratios that were determined from our experimental results. This is potentially useful for understanding the relationship between the bulk composition of a planet and its early atmosphere. We find that the average of these ratios for the outgas and bulk composition are within an order of magnitude, which is, I think, really interesting. A couple interesting things to note are that the C to O ratio flattens after 700 C, so it doesn't change significantly after above this temperature. And the hydrogen to carbon ratio seems to exhibit the most dramatic change between high and low temperatures. So if you know the bulk composition, maybe you can kind of use, and you can measure hydrogen and carbon, then you could maybe use this to say something about the temperature. Just an idea. The study by Mubarak and Kempton that I mentioned earlier found that the carbon to oxygen and hydrogen to oxygen ratios have a strong influence on the cloud chemistry in exoplanet atmospheres. So these experiments that take us, a step forward in building a baseline or a framework that we can compare exoplanet observations to. So this is like really new. This is so Maggie is currently analyzing the residues from our outgassing experiments using ICP-MS, which is basically a different type of mass spectrometer. And we're doing this to understand the outgassing behavior of species like sodium and iron, which are shown in the light thin lines here in the models. So the models predict that sodium, iron, and nickel should also be outgassing. And that's interesting because these components, gas components, would be more readily linked to the bulk composition of an exoplanet. So we analyze the bulk composition of our residues to see how the abundance of these elements are changing as you increase the temperature. And this is just really, really preliminary. This is my first time presenting this. So this is showing the concentration of the different elements versus the temperature. So unheated to 1,000 degrees C. And for the most part, you don't, in this specific experiment was done under atmospheric pressure. And so for the most part, we don't see any variations in the abundances of these heavier elements, except for sodium, which basically outgasses almost immediately, which I think is really interesting. Something we need to think about a little bit more, but sodium by 400 degrees C, sodium has basically been completely outgassed. So it seems like it's outgassing faster than what the models predict for sodium. This one is not as pretty as our atmospheric experiment. So this one was done under vacuum. So one of the issues you'll notice is that aluminum shows a lot of variations, which I can talk about later. But the thing to focus on, I think the thing that's most interesting is that the sodium, again, outgasses almost immediately. And then zinc also basically outgasses completely by like 700 degrees, or sorry, before 800 degrees. So the experiments were done at these intervals, but so by 800 degrees, you don't have any more zinc. So yeah, so I think this is really interesting, and they're different than what the models show, and so that will be really informative. Okay, so here are some important considerations based on common questions I've received about this work. So one question is about the pressure and how that influences the gas composition. So these experiments are done under vacuum, which is not really ideal for trying to understand atmospheres on larger planets. But, this is something we definitely need to look into more, and we've started to do that, doing these experiments at different pressures. But the models by Schaefer and Fegley, they found that the pressure doesn't change the results significantly. What about all the other variables in our experiments, like the heating rate and the grain size? Yes, these are things that we really need to look at more systematically. And that's being done currently, especially with the grain size. We need to look into this more, but for now, our current parameters for our experiments seem to provide results that are similar to the models in many respects. And so that's really helpful for comparing experiments to the models. Another comment that I've gotten a lot is about when you're building a planet, the planetesimals lose volatiles as they're being heated, they lose volatiles. How does this affect the results? So our experiments for instance, our meteorites, they've lost volatiles before they've gotten to us, you know. So our experiments cannot account for what has already been lost. Those volatiles may have been lost before the planetesimals were accreted onto a planet. And so in the sense that if volatiles that are lost before they're accreted on, then that's not really, they become irrelevant in terms of trying to understand the initial composition of a planet's atmosphere. But you know, this study would really benefit from a closer collaboration with the dynamicists, which is something I'm working on. And then another question that I really think is interesting is basically why meteorites? You know, are they really representative of extrasolar planetesimals and the building blocks of exoplanets? And so I'll spend the rest of my time discussing this. So just to rephrase it, maybe say it in a different way, it might help. So can meteorites and the planetesimals they represent be used as analogs for studying planetesimals and planets around other stars? And to answer this question, really, we look to the composition of stars because that is the most direct way to study the composition of the planetesimals that formed around them. Here is a plot, maybe familiar to you. It shows the abundances of elements in the sun versus the abundance of elements in CI chondrites. And it shows basically a striking similarity between the compositions of chondrites and the sun's photosphere. The close agreement between the composition of the sun and the chondrites indicates that the bulk composition of the protoplanetary disk where planetesimals formed was very similar in composition to the sun. So you can use the composition of the host star to constrain the composition of the planetesimals that formed around them. In green, I highlighted the elements that can be measured in other stars besides the sun. So you can see that astronomers can measure an impressive number of elements in other stars, though the precision is not as good as what we can do for the sun. Meteorites exhibit a wide range of compositions, as I mentioned earlier, and that indicates that the exact composition of a growing protoplanet or a growing planetesimal and planet not only depends on the bulk composition of the disk, but on the conditions in the disk, such as temperature and oxygen fugacity. Overall, studies have focused on 3 parameters when trying to understand the composition of extrasolar planetesimals. That's the iron content, the magnesium to silicon ratio, and the carbon to oxygen ratio. The iron content has been shown to correlate with the composition of many heavier elements, like elements heavier than hydrogen and helium. So it's really useful for estimating the composition of the abundance of other elements that may be more difficult to constrain than iron. The magnesium to silicon ratio controls what type of silicate minerals form, such as olivine or pyroxene. And then the carbon to oxygen ratio also controls what types of minerals form, whether they're carbides or oxides, like most of the material in our solar system. So oxides are like most of the material in our solar system. So this example, this shows, this plot is from Bond et al. 2010, and it shows simulations for a planetary system around HD 72659. And they find that terrestrial planets that form within 0.6 AU are enriched in aluminum, while those that form beyond this have compositions that are more similar to the Earth. which is shown in this inset. So basically, the conditions in the disk and where in the disk matters for what the bulk composition of your planet will be. So now I will discuss, so basically I'll summarize what we know about the composition of sun-like stars, general population of stars with planets, and white dwarfs. And so this is just showing where the sun fits into the in categorizing stars. So first we look to sun-like stars or solar twins. These stars are categorized based on a number of parameters, including the surface temperature and the age of the star. So looking to solar twins is an intuitive first approach. If the composition of the star is similar to the sun, then the composition of the planetesimals could have been similar to what we have in meteorites. So here's a plot showing the abundance of different elements in solar twins relative to the abundance of iron. And these values are for an average of about 11 solar twins. So on this plot, 0 means that the solar twin and the sun have identical abundances of a specific element. And the x-axis shows the condensation temperature. Overall, studies like this one indicate that the composition of solar twins and the sun are actually very similar. The range in these abundances are very limited compared to a more general populations of stars, which I'll show you on the next slide. So at least for sun-like stars, meteorites could be used as an analog for the planetesimals around these stars. So this plot from Gonzalez et al. 2001 shows carbon relative to iron for a more general population of stars, specifically those with exoplanets. The blue shaded region shows the full range observed in sun-like stars for all elements. So you can see that the composition of solar twins is more limited compared to the more general population of stars shown here. So studies find that the C/O ratio has the strongest influence on the types of rocks, planetesimals, and planets that form. So here are the C/O ratios for a variety of stars with planets. The sun is at 0 on this plot. And stars that have lower C/O ratios than the sun have more oxidizing conditions and produce minerals and rocks that are more similar to those in our solar system and common in meteorites. While those that have higher C/O ratios have more carbon and less oxidizing conditions. Overall, many of these stars have C/O ratios similar to the sun or consistent with oxidizing conditions. So in this case, meteorites could be fair analogs for planetesimals around stars with sun-like C/O ratios or stars with relatively low C/O ratios, so oxidizing conditions. Finally, white dwarfs are small and faint, but they are extremely dense. They have very strong gravitational fields such that elements heavier than helium should sink rapidly below the surface of these stars. But astronomers have observed elements heavier than helium in some of these white dwarfs and they're called polluted white dwarfs because this is attributed to planetary material falling onto the stars or being accreted onto the surface of the star. Studies indicate that the material accreting onto polluted white dwarfs is similar in composition to terrestrial rocks and similar in mass to asteroids. So this plot shows the composition of material being accreted onto 10 white dwarfs compared to the bulk composition of the Earth and cometary material. And you can see that overall, the material is similar in composition to terrestrial rocks and not comets. So again, this is more support that meteorites, which, when you heat them up, you can produce material similar to terrestrial rocks like the Earth, So meteorites, this is more support that meteorites could be analogs for material around other stars, because they're the building blocks of the Earth, right? So they produce terrestrial-like rocks as seen in these white dwarfs. To conclude, the meteorites are useful as analogs to extrasolar planetesimals. And this is particularly the case for sun-like systems, so sun-like stars and stars with C/O ratios that are consistent with oxygen-rich environments. So meteorites can be used to put constraints on the composition of exoplanets and their initial atmospheres. So the type of experiments that we're doing, where we're using meteorites as an analog to the bulk composition for exoplanets, is a fair starting point. Not only because the samples are, available for direct analysis in the lab, but also because the compositions of stars support that terrestrial-like material are fairly common around other stars. So we will continue this work by analyzing a wide range of meteorites, which tell us about the early atmospheric composition of planetesimals forming under various conditions. So analyzing a wide range of meteorites can tell us about the formation of atmospheres under different compositions, so bulk composition and oxygen fugacity conditions. My student is currently working on analyzing the composition of residues, so we're still working through that data. And so the reason why that's important is because we want to understand sodium and iron and nickel and these other heavier components of the gas that are more directly tied to the bulk composition of a planet. So I envision that the meteorite outgassing experiments and the models will kind of work together to help us to understand the early atmospheres under a wide range of conditions. And this can be used as input into exoplanet atmosphere models, or as a baseline for comparison to exoplanet observations. I'm especially interested in using this work to determine important tracers for the bulk composition of the atmosphere and the planet. So for this, we basically need, what we have here is like a discussion between interdisciplinary discussion about what is actually feasible in the near future, which I've been doing with many of the people I met with today, which is great, thank you. And ultimately, this work could help us to better understand the diversity of exoplanets that are being observed and their potential for harboring life. So for instance, if we understand the stellar composition and the disk conditions, we can use meteorite outgassing to say what kind of atmospheres we expect from planet formation and accretion. So just from building the planet, and then compare that to the atmospheric evolution models and to what's observed. And we can see whether some features can be explained by just accretion and planet formation, or do some signatures need to be explained by some other process, maybe biogenic processes? And so that's all I have. Thank you. Thank you again.
Awesome. Yes, everybody please throw up your clapping emojis. That was really fun. And yeah, I can see a lot of potential for laboratory and modeling synergy coming out of this. We have some time for questions. So if you have a question, you can raise your hand. You can find that button under the Reactions tab, or you can type your question into the chat box. All right, looks like Maxime would like to ask a question. Go for it.
Hi, thank you very much. That was really interesting. I was wondering if you could comment on the fact that often people who look at early atmospheres and outgas atmosphere look at what you can outgas from magma ocean. And here it seems that your work is more in the previous phase where you would outgas during the heating. And in your experience, you go up to 1200 Celsius, I think. So I was wondering if you would expect a change in the outgassing regime when you start to melt material, and if you could be able to maybe predict what would be the atmosphere at the beginning of the magma ocean phase.
Yeah, so that's something we're working on in terms of being able to increase the temperature so that we have melting in our experiments. We actually have some preliminary data, but I haven't looked at it in that sense. In our preliminary data, I don't remember seeing any drastic change, but I can't say right now off the top of my head. But that's definitely something that's very important. And that's another thing that has come up quite a bit in terms of, first of all, can you have an atmosphere before the magma ocean phase? And then what happens to that during the magma ocean phase? So I think I agree that that's all very important, and that's something that we're looking into. But our current experiments don't really address melting. But you could kind of think of it as like this. So if you're modeling this process, you have an atmosphere prior to magma ocean, the magma ocean phase of planet formation, maybe. Yeah, this is why I think working with dynamicists is going to really make this collaboration much stronger, because I have not worked in the dynamical part of it yet in terms of how relevant are these experiments for specific phases of planet formation. So at least for the conditions we're working on, for what I've presented today, under vacuum, it's saying, what would you expect if you allow the planetesimal to outgas under vacuum? But once you increase the pressure, you might some gases may not outgas as readily when you increase the pressure. But that's I see this also being data points for models where you can maybe extrapolate what you expect. So you have an experiment that gives you some constraint, and then maybe you can extrapolate to higher temperatures or higher pressures.
Okay, thanks. Yeah, that looks really interesting. Looking forward to see what your results are.
All right, great question. Auntie, you're next.
Yes. Hi, great talk. Thank you. I was wondering about the sodium, because sodium first, it's present in chondrules. So I was very amazed to see that it evaporates so quickly, because I mean, with those results, it seems like it should be present in chondrules, for example. Mm-hmm. And and I mean, related to sodium it's present in it is present in the planets in the solar system. So how is it possible that this so highly volatile? I mean, it seems like it will go at the first blow, and then it is there. It is in the planets. So how do you can explain this?
Yeah, and I you know, these samples, these experiments were done with CM chondrites, which have, so it's present in chondrules mostly as glass or feldspar, plagioclase, right? So it's in specific minerals. And I know with CM chondrites, they have experienced more alteration. And so maybe it's, so I'm not sure. One of the things that we're missing with these experiments right now is the XRD portion of it, where we look at the mineralogy and look at how the mineralogy is changing. So that would help with better understanding what is the host of the sodium and what is happening to it, right? Okay. What is the mineral host? But from my experience with working with CM chondrites is that they have experienced more fluid alteration. That's part of why they have more volatile components. And so, you know, so if they have plagioclase, maybe there's less of it, or it's in some other form. I think that's a good question for, that's a good question. I don't really know yet.
Thank you.
All right, thank you, Nancy. I think we have time for just one more question. This one's coming from the chat. Evan Davis says, great talk, Myriam. How does meteoric or interior outgassing compare to atmospheric accretion from the gas disk early on in planet formation? Does one control atmospheric composition more than the other?
Well, it depends on the size of the planet and how, so the size and how early, I think it's mostly the size, but I think also maybe how early it forms. So for instance, if it's a gas giant, then the material from the disk is going to be your atmosphere, which will probably be mostly hydrogen and helium. And if it's a terrestrial planet, like Earth size, then it's going to be hard for the terrestrial planet to hold on to, first of all, since it's smaller, it's just not accreting as much of the, it's not holding on to as much of the gas from the disk. So it can hold on to some, and there's some schools of thought that that say, like for instance, the Earth's water was, it accreted its water. Its water, it comes from direct accretion, like the material accreted, whereas some people think the water is from, you know, exogenous material being accreted later. So I think that question basically depends on the size of the planet. For rocky planets, the ones we care about, it's going to mainly be from the outgassing of, over the long term, because those smaller planets can't hold on to that hydrogen as long, and it's basically over the long term, the outgassing of material either from internal heating or from accretion, that is going to be the main source of the atmosphere.
All right, thanks for the question, Evan, and thank you once again, Myriam, for a great talk. Everybody, let's thank our speaker one more time with your clapping emojis. This is the end of our colloquium series for the spring. We'll pick back up in the fall. It's been my pleasure to be your host this quarter, and I wish you all a safe and happy summer of sciencing. Bye, everyone.
Thank you. Thank you, everyone.
Thank you.